Hello, and welcome to this film, which is all about limiting reagents and calculating what the limiting reagent is in a chemical reaction. It could well be that you've got here quite quick to this film, that is to say you've watched a lot of the quantitative chemistry films quite rapidly. I would urge you to check that you are at home with all the stuff that you've done up to this point. The problems seem like they're manageable, and almost that they're getting easy by now. Okay, before you move on any further, because if you try and bite off a bit more than you can chew, you can find that not a lot of it will sink in. Okay, hopefully by the end of this film, you'll understand what we mean by a limiting reagent and what we mean by an excess reagent as well. And when you see a question, you might see some of the signs that you're looking for to spot that it's a limiting reagent calculation. And we're going to do a couple of practice calculations using two different methods, okay? And hopefully we'll see that really and truly, although these are slightly different to the mass-to-mass calculations that we've been looking at in the previous film, there's an awful lot of similarities. Okay, first of all, to try and understand what we mean by a limiting reagent, the limiting reagent is the one that runs out in a chemical reaction. Now, I've tried quite a few times. Presumably I'm failed because I'm not imaginative enough. But I've tried to imagine other analogies that work for this, everyday kind of analogies. The only one I seem to be able to come up with is sandwiches. But anyway, if I was making ham sandwiches, I suppose the very least I'd need to make a ham sandwich would be 2 slices of bread and a slice of ham. Now, if I had 10 slices of bread and 3 slices of ham. Now, assuming I'm not allowed to divide these up into smaller amounts, like I'm not allowed to change the formulas in a chemical equation, I'd only be able to make 3 ham sandwiches, okay? Because my 3 slices of ham would run out before my bread ran out, right? I'd only need 6 slices of bread to make 3 ham sandwiches, right? So in other words, my slices of ham are my limiting reagent here, whereas the bread is in excess because I've got more than enough of it, right? Similarly, if I had 2 moles of slices of bread, I mean, clearly that is a fantastic quantity of bread. But if I had 2 moles of slices of bread and 6 moles of slices of ham, which equally is a lot of ham, okay, how many ham sandwiches would I be able to make? Well, I need twice as many slices of bread as I need slices of ham, right? So I'd only use up 1 mole of slices of ham. In other words, in this case, my slices of bread are the limiting reagent, and my ham is in excess. In fact, I'd have 5 moles of slices of ham in excess, which would presumably feed the population of the world for quite some time. But anyway, I could then decide how many sandwiches I could make, because it's going to be determined by the thing that's going to run out first. In this case, this is my slices of bread. If I can make 1 sandwich from every 2 slices of bread, then I'd be able to make 1 mole of ham sandwiches from 2 moles of slices of bread and 6 moles of slices of ham. Okay, so hopefully that explains what we mean by a limiting reagent and an excess reagent. It's brought into it the concept of moles as well. So let's have a look at a couple of examples. First of all, I'll say, how can we spot a limiting reagent question? Well, if you remember, in the mass stoichiometry questions that we've just been looking at, we're told about the mass of one thing and asked to find out the mass of another. Well, here I'm told about the mass of, where's my pen gone? There. My mass of calcium is given to me. The mass of water is given to me as well, and I'm asked to find the mass of calcium hydroxide. Okay? So, in other words, warning signs for a limiting reagent question: you're given the mass of 2 different things and asked to find the mass of another, rather than the mass of just one thing and find the mass of another. Okay, so let's have a look here. First thing I have to do here is find the number of moles of both of these. So the number of moles of calcium, well, that's equal to the mass divided by the molar mass, which is 10 over 40.08, and to 2 significant figures, that's 0.25 moles. How much water have I got? How many moles, number of moles of water, is equal to 20, which is the mass, divided by the molar mass, which is 18.016. I'll do that one in my head, so I wrote down the answer, and that's 1.11 moles. I'll do that in my head because it's just 1 1/9, but anyway, I suppose strictly speaking that should just be 1.1 moles to two significant figures. But anyway, pretending I hadn't made that mistake, if we have a look at the balanced equation now, 1 mole of calcium requires 2 moles of water, and therefore 0.25 moles of calcium would require 0.5 moles of water. But I've got 1.1 moles of water, so I've got more than enough water. In fact, what we can say here is that the calcium is going to run out first, and so it's the limiting reagent. The water there's more than enough of, so it's the excess reagent. Okay? And in deciding how much calcium hydroxide will form, well, I have to base that on the limiting reagent, because it doesn't matter how much water I add here. If my calcium has run out, it doesn't matter if I add 1,000 moles of water, it's not going to produce any more calcium hydroxide. Okay? So now I can write an expression linking the number of moles of calcium hydroxide to the number of moles of the limiting reagent, and in fact it's 1:1 here, so the number of moles of calcium hydroxide is equal to the number of moles of calcium. Remember, I've chosen calcium because it was the limiting reagent. The number of moles of calcium is 0.25, so the number of moles of that is 0.25. And the mass is equal to the number of moles times the molar mass, which in this case is equal to 0.25 multiplied by the molar mass of calcium hydroxide, which I think I wrote down. Well, I didn't actually, but I put the working down, so that's 40.08 for calcium, and 2 times O plus H, so 2 times 17.1. And if we plug that sum into our calculator, we find that that's 19 grams. And again, that's two significant figures. I actually got an answer of 18.525 later. Okay, but I'm rounding that to two significant figures because my data is too significant. Okay, so very much like a mass-to-mass stoichiometry question, except this time I found the number of moles of both of the things that I was told the mass of before trying to decide which one would run out first, and then basing the mass of my other substance on that number of moles, the limiting reagent. Okay, now I kind of used a bit of mental arithmetic in that one to solve it. So in this method, I'm basically doing a very similar calculation, but I'm going to use a slightly different method for deciding which one the limiting reagent is. Okay, this is for people who maybe don't like trying to do things in their head. Okay, so this time I'm told I've got 1.02 grams of propane. Okay, there it is, and I'm burning it in 5.67 grams of oxygen. What mass of carbon dioxide is what I'm being asked to find. Again, two different masses I'm told, finding the mass of another, so it's probably a limiting reagent question. Now this time, as before, I still have to find the number of moles of both. So the number of moles of propane, number of moles of C3H8 is equal to 1.02 divided by the molar mass of propane, which is actually 44.11. So that would be 3 carbons and 8 hydrogen. And if I do that on my calculator, then that's 0.0231. I could also find the number of moles of oxygen. Okay, and that would be 5.67 grams divided by 32, because that's the 2 oxygens there. Remember, I'm finding the mass of 1 mole, not the mass of 5 moles, so I disregard that 5. Okay, and I put that in, and that's 0.177 moles. Now I could do this, if I'm comfortable, using mental arithmetic and knowing that there's 1 mole of that to every 5 of that in my balanced equation. Okay, but what I'm going to do now is I'm going to compare the actual ratio to the ideal ratio. And I'm also going to show you that it doesn't matter which way round you do things. Okay, and so this is a kind of a foolproof method. Now, if I take the number of moles of propane and divide it by the number of moles of oxygen, 0.0231 over 0.177, That's the actual ratio of these two substances that I had. If I compare that to the ideal ratio, that is the mole ratio in the equation, as long as I get these two numbers the same way up as these two numbers, so I had the propane on top, so let's put the propane on top here, 1/5. Now, this number here equals 0.2. This number here, I can tell you, equals 0.13. So this tells us that the ideal ratio is bigger than the actual ratio. So in other words, you could say that this number on top here is not big enough to make this ratio as big as the ideal ratio. So in other words, this number here is not big enough. There is not enough propane to react with all the oxygen. So that's our limiting reagent. Okay? Just to prove that you could do this the other way around and why it's a kind of foolproof method, if I decided that I was going to put them the other way up to find the ratio, 0.177 divided by 0.0231, compare that to the ideal ratio, which would be 5/1 this time, because this time I put the oxygen on top and the propane on the bottom. This number here is equal to 7.66. This number here is obviously equal to 5. So the actual ratio is greater than the ideal ratio. So this number here is bigger than it needs to be to get to the ideal ratio. So there's more oxygen than there needs to be. It is the excess. Okay, and it doesn't matter which way round I put those numbers, as long as I'm consistent, I should get exactly the same answer. Now, just remembering here that the propane was the limiting reagent, and that there was 0.0231 moles of it. Let's get rid of all that writing there. And the number of moles of propane is equal to 0.0231 moles. I'm using that because it was the limiting reagent. What mass of carbon dioxide will form? Well, let's just write an expression for the number of moles of carbon dioxide, because to find its mass, I need to know its number of moles. I'll compare that to the number of moles of propane. This statement is not true. The number of moles of carbon dioxide, which is 3, is not the same as the number of moles of propane, which is 1. In fact, it's 3 times greater, 3/1, times as big as the number of moles of propane. So that is 3 times that number, which is 0.0693. And now I can go ahead and find the mass of carbon dioxide, because that equals the number of moles times the molar mass, which is 0.0693 times 44.01. Just done that because I remember it, but it's 1 carbon and 2 oxygens, and that equals 3.049 grams, which is 3 significant figures here, 3.05 grams. Okay, so a different way there that doesn't really involve any mental arithmetic, and it's kind of foolproof, but it doesn't matter which method you use, just so long as you make your working clear, because remember, they do award marks for working. So that's the end of that film. Hopefully, if you look at what your objectives were at the start of it, hopefully you feel comfortable with those things. Any questions, as usual, come and ask me or post a comment on YouTube.